So, today's lesson, we're going to start off talking about apparent weightlessness. And then eventually, we're going to apply what we learned to elevator problems. And that's when you're going to get a chance to ride, in the elevator. So, before we get started, I wanted to show you this clip of astronauts floating weightless on the International Space Station. You got to realize that this International Space Station is orbiting the Earth as we speak. And there's astronauts up there. Sometimes they're American, sometimes they're Russian, sometimes they're Japanese. That's why it's the International Space Station. It's a world science project. And up there they do scientific experiments. And they constantly, do maintenance. And this International Space Station, it's a monster. If they set it down, like on the field over here, it would take up the whole football field. With all the solar panels and everything else. So let's take a look at this. I actually have to switch machines because I can't play YouTube on my laptop. So the question is, are the astronauts truly weightless? They definitely appear weightless. They definitely feel weightless. If you put a bathroom scale, you anchored it to the floor of the space station there, they would just be floating right above it, and they would look down and they'd say, apparently I'm weightless. Newscasters will say, look at the weightless astronauts, But what we're going to find out today is they're not truly weightless. Even though it feels like they're weightless, they still have a very significant force of gravity pulling them down. So, in order to understand this, let's think about the inverse square rule that we learned about, yes? So, basically, with the inverse square rule, if you double the distance between the two objects, and if the two objects are, the Earth and you, if you double the distance, and instead of being 4,000 miles from the center of the Earth, if you went out here, if you were 8,000 miles, well, let's say you weighed 100 pounds. How much would you weigh when you're out here? 25 pounds, yes? Because if you double the distance, it's called an inverse square law. What's the inverse of doubling? What's the inverse of 2?
4.
1 half. So the inverse of 2 is 1 half. And then if you square 1 half, you get 1/4. So if you double the distance, your weight would be 1/4. So even if you doubled it and you went out here, another 4,000 miles above the surface of the Earth, if you weighed 100 pounds here, you'd weigh 25 pounds out there. You wouldn't be weightless. You'd still have weight. You'd weigh a lot less, but you still have 25 pounds of force pulling you down, yes? Well, the International Space Station, it's nowhere near up that high. It's only like 200 miles above the surface of the Earth. So those astronauts, they still have lots of weight. Their weight isn't even quartered. It's much less, it's much more than that. So, again, we have to figure out what's going on with this conflict, because we saw them look weightless, they feel weightless, but yet we know that there still is a force of gravity pulling them down. So, to answer this question, we have to learn the difference between true weight and apparent weight. So if the astronauts in the International Space Station are only 200 miles above the surface of the Earth, why do they appear weightless when we really know they're not? In order to understand this, folks, I'm going to do a comparison with a building that has an elevator shaft and an elevator in it, yes? And up above, we have the International Space Station. Okay? Now, let's say the International Space Station was coming around in its orbit coming around in its orbit, and right when it got here, yes? Right when it got here, let's say the elevator in this building, of course this is not the scale, the elevator in this building, the cable breaks, and it starts to free fall down towards the earth. Yes? Now, the truth of the matter is, all elevators have safety mechanisms that would lock them in, and, there's no one single cable breaking and the thing going down. But for learning's sake, let's say there was a person in the elevator, and there's a person over here in the International Space Station. As the International Space Station comes right above the building, coincidentally, the elevator cable breaks. Well, the person in the elevator, yes, if they happen to be like a physics geek, let's say they're standing on a bathroom weight scale. Then you just always like to see how much they weigh when they're in the elevator, yes? If the cable breaks while they're in the elevator, they'll start plummeting down towards the center of the earth. Basically, it would be like the floor dropping out from underneath them. They would be like floating inside the elevator, and they would look down, and what would the scale read as they plummet to the earth? It would be 0. There'd be, oh my God, apparently I'm weightless. Now, they're not really weightless. Gravity's pulling them down, fortunately probably to their death. Okay? But do they feel weightless? Absolutely. And that's what's going on with the elevator and the International Space Station. Just like the free-falling elevator, the International Space Station is also in a state of free fall. And the people inside the International Space Station, they feel just like the person inside the falling elevator. They're like, whoa! Is gravity pulling down on them? Absolutely. Just like gravity's pulling down on the free-falling elevator. Why doesn't the space station then crash into the earth just like the elevator? Go ahead.
Well, the space station has a perpendicular vector going in the y direction and a perpendicular vector going in the x direction. So the reason why they're still feeling the same acceleration or same pull of gravity that an elevator goes down with, but because of the horizontal velocity that's going at that perfect tangential velocity.
Exactly. Okay? It has that perfect tangential velocity that way. I want to show you two scenarios. Okay? One scenario, as the space shuttle, or as the International Space Station is coming around, right when it gets above the building, the cable breaks, yes? But in this scenario, right when the International Space Station comes over top of the building and the cable breaks, I'm going to be like bewitched and I'm going to shut off gravity. Yes? If I shut off gravity, if I could somehow magically shut off gravity, as the space station is coming around, going right there over top, I shut off gravity, the cable breaks. Let's take a look what would happen there. Let's see, what do we have here? Let me get that out of the way here. The person inside the elevator appears weightless because he is free falling towards the earth. The person inside the elevator appears weightless because he is free falling towards the earth inside the elevator, which is free falling towards the earth. Astronauts appear weightless because they are free falling towards the earth inside the International Space Station, which is free falling towards the earth. Why don't the astronauts crash into the earth like the person in the elevator? The astronauts, yes. No. Let's just pay attention. You have to write all these. The astronauts and the satellite have a tangential velocity that the person in the free-falling elevator does not have. Okay, what would happen if there was no gravity right when the space shuttle was orbiting, was right above the elevator, and the cable broke? What would the elevator do if at that instant, there was no gravity.
Was it going up or down?
It was just stationary there.
Okay, so it'll just stay where it is.
It was just going to stay right there, yeah. And what would the International Space Station do?
Going,
It would not have an orbit.
it would just keep going straight line.
All right, let's see what happens. Bye-bye. Broken elevator would not drop. Space station would just continue with the same velocity. But there is gravity. And this is what actually happens. Yes? That gravity pulls in on the elevator, and it pulls in on the International Space Station.
The elevator helps us.
Yeah. I should make it more violent. So, ladies and gentlemen, those astronauts that you saw, they still have weight. They have a weight force providing the centrifugal force that keeps them in orbit. Yes? It's just that they're free falling inside the space station, which is free falling, so they feel like they have zero weight, just like the person inside the elevator. Now, there's no way of experiencing this here on the surface of the Earth. There's no room you could walk into and hit the button and shut off the downward force of gravity. There's nowhere for the astronauts to actually train with that experience, unless they get into an elevator and cut the cable. Okay? But that has its disadvantages. However, NASA has another way of training astronauts. They use a big, I don't know if it's a 747 plane, but humongous jet plane. They go very, very, very high, and then they go into a state of free fall. As they're in a state of free fall, all the passengers on the inside are like, whoa! And they feel like, I think 30, 40 seconds of that free fall.
Isn't it kind of like that? You know that in the carnival they have that thing where you go up and then it's not really going.
I'm not sure. I'm not sure what you're talking about.
It's a ride that I talked to.
Did it just drop you?
Yeah.
And it was just free falling?
The drop, the tower lifts you up slowly, and then you get to the top, it drops.
Well, if you went on that ride and you took a bathroom scale and you put it on the seat, and then you buckled in, and then as you're going on a ride, you kept an eye on the scale area. As the ride dropped down, if it was truly in free fall, if you looked down, guess what the scale would say? Zero. Yeah. Oh my God! Apparently I'm weightless. Yes.
If they were in the plane, what would stop them from putting their legs in the top of the plane?
Okay. The same force that's pulling down the plane is also going to be pulling down them, the force of gravity. And remember, we learned how it doesn't matter if it's a big mass or a small mass, the acceleration is the same. So they all accelerate at the same rate. Okay? So let's take a look. This has a nickname, the Vomit Comet. These are students from RIT, Rochester Institute of Technology, and they won an engineering competition, and they got to ride on NASA's Vomit Comet.
The thing with it I've heard is like once it's done with the free fall, it has to immediately start going back up, otherwise it will crash into the Earth.
Yes.
I've also experienced like 20, like a lot of G's back from going up. You get to go up really quickly.
Okay, so you pay the price.
So it's not just no G, it's also like a lot. Kind of.
That's cool.
Which is why our kind of helping so many. It's like
I don't know if you ever saw the movie Apollo 13. It's one of my favorite movies. Basically, Tom Hanks and Kevin Bacon and I forget the third actor's name. but many times they're filmed where they're, weightless, or apparently weightless, in a state of free fall. They film in a plane like that. And they can only film half a minute at a time, and then they would have to wait for the plane to get back up again, and then they'd film another half. What's that?
I always assumed that it was like really.
No. That's how they actually did it. All right, so the astronaut's apparent weight is 0. The astronaut's actual weight is not 0. So, what is the difference between apparent weight and actual weight? Here's where you could really start taking the notes. Here's where we're going to get into what we need to know.